Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you.
I think so. Yeah.
The button has been pushed.
Has it been pushed?
Yeah. Do we need to get
I have to say, this is a new color of shirt that you have on today. And
yeah.
It was a little shocking when I first came on because you were online before I was, and I pushed the button to join the session, and there's Jesse with apparently no shirt on, and I was shocked for a minute there. I thought, what is happening today?
It's a little, it's a nice orange, but it in the light right now,
it's more like an apricot. It's an apricot.
Yeah, apricot's a good one. I told my wife that I feel like when I put this shirt on, I like it. It's very comfortable. It's very nice. She bought it for me. I won't denigrate it too much, but I do feel like I'm about to go buy a timeshare after my shuffleboard game when I put this on, just because it gives that vibe a little bit. You know, it's a little bit Jimmy Buffett.
It's older than you.
That
shirt is older than you.
It's a little bit, but I do like it. It's a very comfortable shirt, so. And appropriate maybe for the rocks we're talking about today, which is some old rocks that are forming in Mammoth Cave. That's a bit of a stretch, isn't it? That's a bit of a stretch.
What do you mean? What's a stretch?
This segue. I was trying to segue. Just really, that one didn't come together very well. Old shirt's too old.
No, but I'm excited. Hey, Jesse, for like some of our listeners, I'm excited to talk about sedimentary rocks. I'm really excited about this.
Nice
so
one. Yeah.
Let's give them their fair due.
That's a good point. We are going to spend... Okay, well, let's back out. This is, if you're listening to this in the podcast, this is the second part of our Mammoth Cave National Park series. We're talking about the specifics of Mammoth Cave here, and then part one, go back and listen to that if you haven't, or go to our audiobook on the Camp Geo app. It's the first link in your show notes where you can get all 3 chapters of this book with all the images. We have some really, really freaking bomber images that explain some of the stuff here. But this chapter, this episode, is really covering the rocks and the tectonics, I think, or the setting that makes Mammoth Cave so massive and so special.
I agree, Jesse. I want to give a shout out. Our graphic designers, they do such an awesome job. I mean, it's a difficult task to, convey exactly what we want because these are not geoscientists that we're working with, but man, the images in here and the GIFs that we've put together are amazing.
Yeah, they really help tell the story in a really sort of beautiful way. So let's just sort of summarize where we came from, Chris. We talked last time about the overview, what makes Mammoth Cave special. It's this massive, massive, long cave system. We talked about what you need to form a solution cave, the recipe and the ingredients you need to form a solution cave. Then we talked about karst topography, which is kind of spread sporadically throughout a lot of places in the world, frankly, but particularly here in this part of the world, which is Mammoth Cave National Park part of the world. This is an area of karst topography that covers, 6 different states right there? I mean, it's a huge area.
But look at this a second. It's bigger surface area-wise. This is bigger than the state of Kentucky. This is a huge area. Kentucky is definitely feeling karsty.
It's super karsty there. Exactly. And Chris, you just said it right there, but this is the central Kentucky karst area. It's a limestone belt that extends all over this map from southern Indiana down into Kentucky and Tennessee. Big region of heavy karst topography.
That's where we came from. Today, what we're going to talk about now is we're going to get into a little bit of the weeds, Jesse. I'm going to give you a little bit of leeway here. And actually, I might jump into the weeds with you.
No, Chris, you're going to be slithering around in the weeds with me. Don't give me none of this crap.
That's here. True. That's true. I'm like a water moccasin here in Kentucky. I don't know if they have water moccasins there, but we're going to talk about Mammoth Cave specifics in this episode, which will lead nicely into our third chapter in this sequence on just like what are the cave features then and the types of passageways that you get. So that's where we've come from. This is where we're going. Jess, let's jump. Let's go. Let's start off.
So we talked about the solution type cave. And again, we need rocks that are easy to dissolve. We need a solvent, which is groundwater here with some acidity. We need a hydrostatic gradient or a hydraulic gradient. So we need kind of water moving through the rocks to bring a fresh supply of recipe ingredient number 2. And then we need time. All 4 of those ingredients. How do they come together, Chris? What is Where do we start in this sort of ingredient list?
Here's a catchphrase: old rocks, young cave. And so we need to jump back to when these rocks were formed. And we'll talk a little bit about this later, because this is really your wheelhouse. You're definitely the expert in the room on, radiometric dating things. And we'll get into that later on. But we're talking about rocks that are Mississippian in age. And the Mississippian began about 350 million years ago. But the rocks here, the oldest rocks, began to be deposited about 340 million years ago. But before we delve into like the specifics of those formations, I want to talk about formations in general first, because we do this all the time in geology. We kind of group rocks together and call it a formation.
Yeah.
And that just means that this is a sequence of rocks, vertically accumulated usually, that share common characteristics and relatively common depositional time periods. In other words, we're talking about rocks that didn't have massive breaks in time in between them, massive buried surfaces of erosion.
And these are
we call those formations.
Formations, and they represent a period of time that the Earth was kind of stably depositing the same type of stuff. So sandstones being layered upon sandstones, because the climate hasn't changed, the sea level hasn't changed, etc.
Yeah, this is uninterrupted stuff. Yep.
Relatively uninterrupted, relatively similar. There can be gradients across it, so you can get, if you look at a limestone formation, there can definitely be shale layers in there. That'll be part of the description, though, of the formation. So there's always kind of a gray area in between formations. Sometimes you have really sharp boundaries between formations. Sometimes it's kind of a gradient as it transitions in and out. Here in Pennsylvania, where we do one of our the intro level class field trips, we go see a transition from kind of a shaly carbonate package to a carbonate package. And, that gradient transitions over several tens of meters. We have to break them apart into different formations somewhere. So we kind of put a line in the sand there and say, oh, here it is. And then sometimes you can get really sharp gradients. But Chris, the important thing here is we have 4 formations, and we'll come back to this. But what was going on in the Mississippian? Why the carbonate here?
This is what I love about geology, is trying to imagine each page of the book. What did Earth look like, or what did this part of Earth look like at the time that this was going on? And it's difficult to do this sometimes, but we need you to imagine a North America that didn't look anything like what it does now, both spatially, but also from a climate perspective. I mean, North America, then it didn't resemble anything like it does now, and the climate was dramatically different. I mean, this was definitely a greenhouse climate. There was a lot more carbon dioxide in the atmosphere, and we've talked about this, Jesse, in our podcast several times, and we've done a short book on the carbon cycle and so on. Carbon dioxide sets the temperature. It is the thermostat for our planet, and so things were very different then. And so during this time, it was much warmer. There was a lot of water. The area was covered in shallow seas. And in fact, Jesse, the Mississippian is named after the age of crinoids, which if you look at image number 2, this is a picture of a limestone layer with a crinoid fossil embedded in it. These organisms...
Really quick, let me interrupt. Crinoids are really, really common in rocks of this age. You can go up to Michigan, they're exposed.
Right.
Crinoids are really cool fossils, and they're kind of everywhere. And I don't know, I find them fun, even though they're relatively simple. So anyway, sorry.
No. It's just that these marine organisms, they were marine definitely. These dominated the seas. And I think we do this a lot in geology, was we define time periods by the life that dominated the planet, right? The Cretaceous. That was not named after the age of the dinosaurs. The Cretaceous was actually named after chalk organisms that, were so abundant in every ocean and every corner of the planet. So these deposits were just so prolific that we named an entire time period after them. And we did the same thing in the Mississippian with the crinoids.
So, Chris, let me come back to the what we're visualizing here. What kind of a planet are we visualizing when we're thinking about this? Basically, you take the continent of North America and you raise sea level by several hundred feet. So the continent, the low-lying interior parts, Michigan, Kentucky, Indiana, Iowa, they're flooded. The Canadian Shield, it's flooded by the ocean, and it's a lot warmer. Like you said, the ice caps have melted. It's a warmer environment. So basically all of the flat-lying area in North America was flooded by this shallow interior sea. You have delta environments. You have rivers meandering around marshy wetlands. That's kind of what we're picturing here in the entire inner part of the North American continent.
That's right, Jesse. So, you know what we should do, Jesse, is we should at least name the 4 formations that are at play here. And I want everybody to keep in mind that this is not a scientific textbook on the geology of Mammoth Cave. I mean, we're not going to go into the weeds on the rock formations in any way that we could. This is for everybody.
That's right, Chris.
So that you can just kind of appreciate what you're looking at when you're in and around the Mammoth Cave area.
And I think, Chris, so that I like the way you said that. Let's keep it kind of simple. We don't need to get into the weeds about the specific differences between the St. Louis and the St. Genevieve's formations. Like, we will touch on that, and you'll know enough to be dangerous when you're going in the cave and you see the cave. But it shows the 4 rock units that are important here. And really, we're going to break them into 2 categories. The bottom 3 are all one group, and the top one is a different category. Chris, like, why? Why do we, when we're talking about this, do we say, oh, we're going to group the bottom 3 together and the top one separately? What's the difference?
I think, Jesse, first, let's name them from bottom to top, from oldest to youngest. So we're talking about the St. Louis Formation, the St. Genevieve Formation, the Gherkin Formation, and the Big Clifty, which, by the way, the Big Clifty is my favorite just because I love the name of it.
It's such a great name.
And
it's so descriptive. I love it. It's great.
Yeah, that's right. The first 3, the oldest 3, in other words,
hold on, Chris, let me interrupt
3.
here. When you say first 3, we're going in time. So we're, again, going oldest to youngest, which is bottom to top here. That's how geologists think
bottom
about
to
this,
top.
Right? So we're going to do the same thing, bottom to top.
That's right. Excluding the Big Clifty, because that's the top 4th formation. Talking about these bottom 3 layers, this is where the largest caves formed. They formed in the St. Louis Formation. They formed in the St. Genevieve. They formed in the Gherkin Formation because these are limestone rocks. These are the rocks that are the first ingredient that we talked about in our prior episode.
Recipe ingredient number 1.
Rocks. You got to have that. That's right. It's a huge piece. But the Big Clifty is super important because this one is different. The Big Clifty is made up of shale and sandstone, and these are chemically different. These are chemically relatively stable rocks. In other words, they're not susceptible to dissolution. These are rocks that are not going to get dissolved readily at all. So they kind of form this ceiling, and that's really going to become important in the formation.
Chris, I love that you use the word ceiling right there because I don't want to end quickly, but I'm excited to get to the ending of this episode because if you've been listening along to this, we've been talking about Mammoth Cave, how it's great. It's the biggest cave in the world, like by a huge margin. We haven't answered why. And we're going to talk about that. And the Big Clifty is fundamental to why here. Why did such a big cave network form here and not somewhere else go back to image number 1. We showed you this central Kentucky karst area. Why here and not anywhere else in that area, right? That's kind of a big question. We're going to come back to that. So I love the way you separated those.
So put a pin in the Big Clifty.
Yeah, put a pin in that. Let's go through the first 3, and there are differences, like they are different formations. Again, we're going to stay out of the weeds, but we're going to highlight the differences. So we start with the St. Louis. That's the bottom. That's the first one in geologic time. You said before it's about 340 million years old. It's a cherty limestone. So what's important, Mr. Out of the Weeds Bullheis, Mr. I promise to stay out of the weeds. What's important in that?
Well, what part? I mean, first of all, let's talk about the limestone part, and then we'll dive into the cherty part of it, okay? So we know that this is a marine environment, and I just want to ask the question before we go ahead and talk about the answer to it. But how would we possibly, as geoscientists, know that this is a marine? This is an ocean-type, shallow marine limestone deposit. Well, the reason is because of the fossils that we find within this formation. We're talking about corals and bryozoans and brachiopods and crinoids, of course. We just talked about crinoids. We find shark teeth in this stuff. These fossils are indicative of the environment in which this rock was laid down. And then it also has these lenses of chert in it. And so, Jesse, I'm going to leave that to you. Chert is kind of this niche kind of rock. Talk about chert a little bit.
Yeah, Chris, you're right. Chert, I do like chert a lot. Chert is C-H-E-R-T. That's how we're spelling this word here. Chert, it's like limestone in that it's a chemical precipitate rock, but this time it's just quartz. It's SiO2 is precipitated out, and it can be done a bunch of different ways. On the modern and Phanerozoic Earth, like in the last couple 100 million years, we often think of diatoms, these little organisms that kind of use silica. They make their shells, their bodies, their houses out of silica, out of SiO2, and then they die and kind of drop down and form chert layers. It's not always the case, but the point here for the use of going to Mammoth Cave is that it's not easy to dissolve SiO2. It's quartz. And so you'll see this sticking out of the walls of the cave, these little cherty layers, because it's not being dissolved. The limestone is being dissolved around it. And
it's really hard too.
It's really hard, and it's not being dissolved. It's both mechanically and chemically resistant to degradation or breaking down. So you'll see the chert sticking out. That's kind of the point here.
And Jesse, I just want to interject something for all of the listeners out there. When Dr. Jesse says something like, and he does that with his voice, just sit back and prepare to be doctored a little bit, because that's when he's evaluated. When he does this, I'm sitting back there and I'm just kind of listening to, all right, what am I going to do here? And then I perk up when he does that little inflection in his voice, because then I have to go to work. I have to either keep Jesse in the weeds or get him out of the weeds really, really fast, because he gets long-winded.
Yeah, that's exactly
so
right.
That little inflection is really important. I've learned this over the years of working with you.
That's wise advice to the listener right there.
All right. So Jesse, right on top of the St. Louis Formation is the St. Genevieve Formation. I love the name Genevieve, by the way. My wife is named Jenny, and I call her Genevieve all the time.
Yeah.
There it goes back to an old TV show, but anyway. Yeah. So
we don't need to know too much
Formation,
more in the details there, Chris. Just, there we go. St. Genevieve Formation.
That's right.
The Genevieve Formation.
Yeah, it has limestone and dolostone. And dolostone is a lot like limestone, but it has a slight chemical variation where magnesium ions have substituted for calcium ions in the limestone structure. And so you get this less reactive rock. It just is not as soluble. It has the same hardness and it has the same lithology. I mean, it looks the same, but it is a little bit different. And so really the only other notable thing about this St. Genevieve Formation is that it doesn't have gypsum, and we didn't really mention that as a thing, but it doesn't have gypsum lenses in it like the lower, older St. Louis Formation does, but it does have very similar fossils. So we just have, basically, Jesse, we have shifting shorelines, different fluctuations in sea level, and different fluctuations in the saltiness of the water that was depositing these rock layers at the time.
And we're going to move now, Chris, into the Gherkin Formation, the third one, the next youngest, second to last youngest, but the top.
Sorry, I have a relationship to every one of these names because Gherkin was a middle school science teacher that I had.
Really?
So, yes.
That's Mr. Gherkin. Mr. Gherkin. That's a funny name. So the Mr. Gherkin Formation here is very different, actually. It's similar in many regards. It's the same chemical composition, limestone, CaCO3, calcite for all intents and purposes. It is different, though, from the two rocks below, the St. Louis and the St. Genevieve, because this is now a chemical precipitate, not a biochemical precipitate. There's no life involved. This is what's called a crystalline limestone. It's really deposited almost directly out of seawater. There's not a life intermediary. There's not critters making homes out of calcium carbonate and then dying and then getting deposited on the ocean floor. It's a different mode of formation, and it's more crystalline.
But, Jesse, the upper part of it returns back to being more fossiliferous as opposed to crystalline. And so it is very different in its lithology compared to the bottom two members. But, Jesse, it also has something interesting. It has oolitic limestone.
Oh, I love oolitic
limestone. I do too. I love oolitic limestone. First of all, oolitic is spelled O-O and then litic, L-I-T-I-C, and then limestone. So, Jesse, real quick, no weeds.
Real quick, no weeds.
Limestone.
Promise,
yes,
no weeds. These are basically little balls of calcium carbonate, think of little BBs or little peas that are maybe smaller than peas.
Tiny,
BBs are smaller. They're basically, the idea is they're getting rolled around in like a sort of an intertidal area. As they're getting rolled around, they're getting crystallized. The calcium carbonate is precipitating onto these little things that are rolling around. And so you end up getting this oolitic limestone. Chris, I have seen a crazy rock up in the Yukon that was oolitic magnetite. It was pure magnetite, but it was...
Okay, can I take a crack at this a second? So these were magnetite, little tiny magnetite sand grains that were on the surf zone where the waves were kind of rolling back and forth, right? And this must have been a warm climate in a very salty ocean, because then these magnetite grains got coated, and as the water evaporated, it precipitated calcium carbonate on them, which is limestone, and it forms these little spheres that look like O's, if you will. Imagine an O like a sphere, and that's how I kind of remember oolitic and what it is because of the spelling of it, So
yeah, it's a good one.
Is that what was going on?
It's a good story. I don't actually know. I don't remember.
Well, we're going with mine then.
Yeah, we're going with yours. I see there's, there's an ore deposit as well. So it could be a replacement, like a massive replacement of the original calcium carbonate with magnetite. But anyway, cool oolitic rock. So the Gherkin Formation is an oolitic limestone. And so that's the end. Most of the cave formation is in those three layers, the St. Louis, St. Genevieve, and Gherkin Formation. The Big Clifty, however, even though it doesn't have cave formation in it, it's the youngest formation, it's the top one, and it's arguably, debatably, the most important one for Mammoth Cave. And it is a cap rock. The reason is it's a cap rock. It is not calcium carbonate. It's detrital. It's sandstone, siltstone, shale. It's a variety of those types of rocks together, but they're all different than limestone. And it's not easily dissolved at all by groundwater.
And, Jesse, it is not easily eroded. So, question to everybody, what would have happened to all this cave system that we currently have if the Big Clifty wasn't there?
Oh,
it wasn't
Chris,
there protecting it.
Can we end with that? Because that's such a good question.
Okay.
Let's end with that. That's such a great question that I just want to stew on that. So reiterate that question, and then we're going to come back to it.
All right, we're putting a pin in it. What would have happened to Mammoth caves, okay, because there's a lot in a huge area, if the Big Clifty wasn't there protecting it at the surface?
Beautiful.
Okay?
Let's move on now to the specifics. We're going to zoom in and then we're going to zoom out. This is an hourglass episode here. We're zooming into Mammoth Cave and then we're going to zoom out to that question. In the cave, there's really the beautiful thing, and one of the most spectacular parts about Mammoth Cave is the levels. There's 5 different levels to this cave, or 5 distinct levels. And what we mean is vertical levels. So, think of floors of a big apartment building. There are floors to Mammoth Cave, 5 different
this
floors.
Is a 5-story building.
It's a 5-story building, exactly. And this worked in reverse of the way that geology often works. The top levels formed first, and the bottom levels are currently forming, let's say.
So can I just, I want to come back to that here a second, Jesse, because I think what you said is important to note. The cave levels formed in the youngest rocks. They formed in the Gherkin, then they formed in the St. Genevieve, and then lastly, they formed in the St. Louis Formation, which it would mean the most recent caves are in the St. Louis Formation, but the St. Louis Formation is the oldest rock layer. So that's what you meant when you said this is kind of reverse how we usually work in geology. That's a really good point that we need to emphasize here.
I think the one piece of information that really helps explain how this formed is that the top 4 levels are fossil levels and the bottom one still has water in it. It's quote unquote modern river level. It's where the water is still there.
Hold on. Okay, I just want to be clear. When you say fossil levels, you mean they're high and dry. You're not talking about the actual fossils that are in the rocks, because they're there too.
Yep, exactly.
Okay, Jesse, question for you. I want to ask this, and then maybe you can flip it back to me. What's your takeaway with image number 4, this GIF? Because I think it's really good, but I want to know what your takeaway is on this.
That's a good question, Chris. There's so many good takeaways. Here's what I think is the main point. The main point that there's 4 high and dry. I love the way you said that, high and dry levels. And then there's one active one. I think that's the main takeaway here, because I think that main takeaway helps explain the process really well. What about you? What's your number one takeaway?
So the big river on the left is the Green River, and that's the river that drains this whole part of Kentucky. Okay. The level that the Green River is during this, so you look at frame 1 compared to the last frame in this GIF, this drives where the groundwater flows. It's the level that the Green River is that drives the hydraulic gradient. This is what causes the water to circulate through to dump into the Green River. So as the Green River incises down through the limestone formations, it's causing caves in these formations to be left abandoned. As the Green River goes, the groundwater then is going to drop down to correspond to where the Green River is. That's my takeaway with this.
Can I add one thing to it, Chris? And we're still building to your question that you asked before, but pay attention to the orange layers in this GIF. Pay attention to the top orange layer. That's the Big Clifty. And think about why that might be important for forming Mammoth Cave here. And so with that, Chris, let's maybe just touch on the age. Can we talk about the age of cave formation? Because you said old rocks, young cave before. Let's put some numbers on that. The upper levels of the cave were formed they were fully formed. Let's say that they were kind of mature at around 3.2 million years ago. So that's million years ago. That's a long time. Let's not forget that. That's a very long time. Even though the rocks are 100 times older than that, that's still a long time. So
Jesse, I want to ask, because I think people want to know, how in the world can we put a number on this? What radiometric dating principles are used to put this piece of the story together? So
in caves in general, they're difficult. They're young typically, and so geochronology gets more difficult in some ways the younger you are. And so people kind of throw the book at cave formation. This one is a really cool one though. The caves in the upper levels, we have to remember that those used to be active streams. And so the streams were flowing through crevices in the rocks, actively flowing through. Scouring through. Yep. And there's actually sediment deposits up there. So there's sediment deposited in the cave. And that sediment was derived not from the cave itself, but from up on the surface somewhere, and then brought down in a disappearing stream into the cave and dumped there. So think of like a gravel bar. There's gravel bars in there where there's sediment dumped. Now, because the sediment was at the surface, then got brought in by this active stream, we can use a really cool form of geochronology, which is beryllium-10 dating of quartz. And the way this works is that beryllium-10 can be formed in the atmosphere, and it can be kind of soaked up into different minerals. And so basically the clock starts when the minerals are taken out of the light source, basically, or when they're buried, for instance. So there's also... So this is a form of cosmogenic dating then, right? Cosmogenic, exactly. That's the term for this, is cosmogenic dating, where basically there are radionuclides or radioactive elements produced in the atmosphere that are incorporated, and they start to decay once they're deposited, especially in these dark regions here. So that's the way this kind of works in this area. Okay, so basically what you're saying then is we're going to get these detrital sedimentary deposits that are going to get successively younger as you go deeper and deeper into these levels of caves that are left high and dry. Is that correct? That's exactly right. So you imagine like a quartz crystal sitting on the surface somewhere, a stream, it's exposed to cosmic rays because it's right near the surface, it's at the surface, and it's generating these aluminum-26 and beryllium-10. It gets swept up in a stream, carried down into a cave where it's no longer exposed to those cosmic rays, and the clock starts. It's basically you're flipping the sand dial over at that point in time, and the clock starts. And now we can go and we can look at that sand dial and see how much sand has fallen out of that sand dial. And that gives us some limits on the age there. So that's how we're doing that at different levels of the cave. So we know the fifth level, the bottom one's active now. We know the top one was fully mature 3.2 million years ago. All right. So then, Jesse, just progressing through this story in terms of how Mammoth Cave specifically formed, water worked through this caprock, the Big Clifty,
along cracks and through the pore space and along bedding planes too. You have the Big Clifty is a formation. And so it has, you have these different layers within this one formation. So the water's just kind of taking the path of least resistance. And then when it got to a depth, when it encountered soluble rocks, these limestones and maybe even to some extent the dolostones, it began to dissolve. And this is the work of carbonic acid. And if you point to image number 5 a second in your stack, this is just something that I did in my lab as I took some dilute hydrochloric
Chris
acid.
is dropping acid in the lab over there. We got it on video.
You take a good chunk of limestone, you put it on a lab table, and you put some dilute hydrochloric acid on it, and it fizzes like crazy. And this is every intro level student in geoscience does this at some point. I mean, geologists are renowned for carrying their little bottle of acid with them wherever they go in the field, And so this shows the work of that.
I just want to highlight on that image, on that GIF, there's a spot where you've probably put acid on that sample before and you're putting it in a similar location. There's a little depression, right? And this is the way it works in the cave too, is that there's a positive feedback loop. Water takes the path of least resistance. It'll work its way in a crack. It'll start to dissolve. Once it starts to dissolve, the crack gets bigger, more water goes in, more dissolution happens, and it goes on and on and on, a positive feedback loop. This is the way that Mammoth Cave formed. So we get these concentrated zones with these big, sometimes massive conduits that you'll be walking through when you're walking along the paths in Mammoth Cave. That water can flow through there faster and it can erode and dissolve rock faster. So it just gets bigger and bigger and bigger in this until you run out of water, basically.
It becomes this positive feedback loop where they just kind of come together and you have just this concentration of water, and it creates these channels that are literally channels underneath the ground that just kind of merge together because of positive feedback, scenario that you just walked through. So, and then Jesse, why would these passages be left high and dry? Well, that would be because the Green River is down-cutting deeper and deeper, which creates then a steeper hydraulic gradient. It allows for caves to open up then deeper in the subsurface. The same process just repeats itself.
Same exact process. Let's think now back to the Chris Bullhuis question earlier. What would happen if we did not have the Big Clifty here? In other words, why did Mammoth Cave form here and not somewhere else? So why so big? I think that's let's end with this, Chris. Like, why is Mammoth just so massive? Why is this area just so perfect for building a massive cave?
Are we going to come back then at the end and like make sure we have a solid answer in terms of what would happen without the Big Clifty?
Yeah, I think that's going to be part of this answer. I hope. Yeah.
Yeah. Well, we can kind of go through this point by point, but it doesn't take a lot of time here. Why so big? You got to have a very soluble rock. And the limestone here is particularly soluble. And you know what else, Jesse? Like Kentucky now and Kentucky 3 million years ago, it's very wet. It has a lot of rain. So you have a soluble rock, you have a lot of rain, and therefore you're going to have a lot of carbonic acid, that's dissolved in this water, doing its work, doing what this solution does to limestone.
You have all this jointing. You have lots of places for the water to go, right? And we're going to talk about what's called the Penroyal Plateau. This is a huge component of this. The Penroyal Plateau, it's called the land of 10,000 sinks because this is a huge karst area that does not have the Big Clifty exposed here anymore. And so there's no cap. So the caves there are not caves. They're sinkholes. And so the water is soaking in these sinkholes because it's dropping down into these sinkholes and it's following the hydraulic gradient to the Green River, flowing through this area. So you can imagine how as the Green River downcuts, that water flow gets deeper and deeper and deeper, and you fossilize the top upper layers of Mammoth Cave, and top upper levels there are left high and dry, as you so aptly described.
So basically, Jesse, this water that's doing the work is coming from quite a distance away. It's coming from this Penroyal Plateau. So we're left with tackling the question, right? What would have happened to Mammoth Cave if it didn't have the Big Clifty, if it didn't have this caprock, like the Penroyal doesn't have the caprock?
What would it do? Well, it would be the Penroyal, right? I mean, it'd be the Penroyal. I hope we kind of got there, because it would be the Penroyal Plateau. It would just be sinkholes. It has this stable caprock.
They would have been destroyed.
They would have been destroyed, right? And so
Absolutely.
Because this caprock is here, it's this really solid, really mechanically and physically and chemically solid rock layer, rock unit, rock formation that provides a ceiling. And I mean, really, it's providing a ceiling here. And it's preventing both water from percolating straight down into the cave and sort of, making sinkholes there. But it also doesn't exist in the Penroyal Plateau, so it's not supporting caves over there, if that makes sense, right? It's doing all sorts of stuff, the Big Clifty, that helps support Mammoth Cave and the network that is forming.
That's right. And a couple other just final points here as we wrap this episode up, but Mammoth Cave is not known for tons of speleothems. I'm talking about things like stalactites and stalagmites, which is in episode 3. We're going to talk about these things, but it doesn't have a ton of them, and it's because of the Big Clifty. In order to have these, you need to have water that's permeating from the surface, circulating down through the rock and dripping through these cave openings, but you don't have a ton of that because the Big Clifty protects it. It's relatively impermeable to that kind of action.
Chris, let me explain that one extra step further. We have a lot of laterally flowing water. There's water flowing laterally through the cave system, not like top down like many other caves do. Not groundwater seeping. I mean, that happens too, but not as much. We have a lot more laterally flowing, a river flowing through the cave system rather than it kind of seeping and dripping from the top down.
I guess the last point to make here, Jesse, is what is the future of Mammoth Cave? I mean, let's let that sink in a second. And basically, everything that's happened has been driven by where's the Green River? Where is it at? And so we might get another level of cave formation. The one that it's currently residing might be left high and dry if the Green River continues to downcut, sets a new hydraulic gradient, and leaves where it is right now, kind of abandoned or fossil caves, if you will.
Without anything changing, without climate changing, without, with a constant water supply that we have, with the rocks in place and not tilted or no tectonic activity, it's probably going to keep cutting down. And that's a beautiful thing to imagine. And when you're looking at the river Styx down there in the Mammoth Cave, you might be standing high and dry in a million years, and the river will be beneath your feet there.
Hey, I cannot believe you and I have not mentioned this, but I think we need to, because if there are any geoscientists listening to this, they're thinking Green River, the famous Green River in the western U.S.
The Green River Formation, yeah, totally.
The Green River Formation with all these fish fossils in it and so on. It pertains, it's so intimately tied to the Grand Tetons and so on. Not the same Green River, not even close, different part of the country. So we do need to mention that this is not the same Green River.
Green River. Yep. Well, I think, Chris, that's probably a good spot to end on. The Green River, so important. The Big Clifty, so important. Why is Mammoth Cave mammoth and so much bigger than everything else and so unique in this regard? Well, there's a bunch of different factors, but we've covered them here. We talked about the rocks. We talked about the Big Clifty, how it's supporting. We talked about how it cuts down in this hydraulic gradient. I mean, it's just a very, very cool story, Mammoth Cave National Park. And we got into the weeds a little bit and also managed to stay out of some of the less important weeds, I think, Chris. Yeah,
I think so. And then, hey, up next, our final episode is going to be on cave decorations, what we call speleothems.
Beautiful, beautiful stuff. So, hey, if you listen to this on Planet Geo on the podcast, you can get this episode and 2 other ones with all the images, some really great images we made on the Camp Geo app. Download that. It's the first link in your show notes. There we have a ton of free content, our Camp Geo content, which is basically the class Chris and I teach, intro-level, introductory geoscience at the college level with all the images you need. We also have a bunch of other content, including geology of national parks and some of our other podcast series looped together, including this one on Mammoth Cave. So go there. You can find all 3 chapters with the images you need. You can also go to our website, planetgeocast.com. There's a support us link there. We always appreciate your support. Send us an email, planetgeocast@gmail.com, and follow us on all the social medias @planetgeocast.
Cheers.
Cheers.